The purpose of this training kit is to familiarize you with the emission control systems used on the 1981 AMC and Jeep vehicles. Because these vehicles are equipped with many of the emission control systems used in 1980, this kit deals specifically with new componentry and design changes for 1981. The engine that changes most dramatically is the 1981 258 cubic inch six-cylinder engine. A number of the six cylinders components have been redesigned to trim over 90 pounds from the total engine weight, improve reliability, reduce engine noise, and improve fuel economy. A new aluminum intake manifold results in a 15-pound weight reduction. In addition to its aluminum construction, this new manifold has several other unique design features. In past years, the intake and exhaust manifolds were connected. They are now completely separate from each other. Therefore, exhaust heat no longer serves as the heat source for fuel vaporization. Instead, a coolant temperature passage within the manifold casting allows the heat contained in the coolant to serve as a heat source. An electrically heated warm-up device located in the bottom of the manifold serves as an additional heat source. This warm-up device is energized only when the coolant temperature is below 160 degrees Fahrenheit. This combination of electric and liquid heat provides a very predictable heat input during cold engine warm-up, yet reduces the peak heat during warm engine operation. From an emission control standpoint, this design improves combustion efficiency, which results in a reduction in the amount of pollutants released into the atmosphere. The six-cylinder's camshaft has also been redesigned. The camshaft has a new profile that reduces valve overlap without reducing maximum horsepower. This reduced valve overlap increases low-speed torque and helps the engine run smoother. It also makes possible a lower idle speed than was possible in previous years. This lower idle speed results in a substantial improvement in fuel economy. The recommended curb speed settings for the new 6 are: vehicles equipped with manual transmissions, 650 RPM, plus or minus 70, and automatics, 550 RPM, plus or minus 70. On automatics, the curb speed is set with the transmission in drive. These low idle speeds must be boosted under certain engine operating conditions. Electrical loads require that the idle be boosted so the vehicle's charging system can keep the battery charged. There are only 2 individual vehicle components that tax the charging system enough to require a higher idle speed. One is the new intake manifold warm-up device just discussed. When this device is energized, a boosted idle is needed. The rear window defroster grid also places a heavy load on the battery. So on vehicles equipped with this feature, the idle speed must also be boosted when the grid is energized. There are also 2 mechanical loads that affect idle speed. The idle must be boosted under these loads in order to maintain a smooth, stable idle. The first load condition results from the operation of the air conditioning compressor. The other is the increase in power steering pump pressure that results from an extreme turn. In addition to the electrical and mechanical loads just discussed, there's one more engine operating condition that requires a higher idle speed: cold ambient temperatures, which can result in carburetor icing and fuel condensation problems. The idle speed is boosted under these conditions by a new idle speed control system, which is used on all 1981 AMC and Jeep vehicles equipped with the six-cylinder engine. This new system, which utilizes electronics and intake manifold vacuum to boost the idle speed, is made up of several components. An electronic control unit functions as the system's brain box. The control unit receives electrical input alerting it to the presence of any of the operating conditions requiring a higher idle speed. The control unit then electrically controls the operation of the solvac, which is mounted on the carburetor body. The solvac consists of 2 subcomponents, an electric holding solenoid and a vacuum actuator. The electric throttle holding solenoid is capable of holding or maintaining a preset throttle position, preventing the idle from dropping below a preset speed. However, the holding solenoid can't increase the idle speed. The vacuum actuator is capable of increasing the idle speed. It does this by mechanically moving the throttle linkage, which results in a larger throttle opening. The vacuum actuator receives manifold vacuum from this 3-port vacuum switching solenoid, which allows vacuum stored in a reservoir to reach the vacuum actuator and energize it, thus increasing idle speed. The last component in the idle speed control system is this ambient temperature switch, which is positioned in the air cleaner. At ambient temperatures below 55 degrees Fahrenheit, the switch is closed, grounding its circuit to the control unit. All of the control unit's input and output signals pass through one connector. But for purposes of explanation, we'll use this schematic to illustrate the operation of the system. We'll examine the system's response to the various input: operation of the air conditioner compressor, the rear defroster grid, the intake manifold heater, ambient temperatures below 55 degrees, and finally the coil's input on engine RPM. Here, no idle boost is required. Therefore, the Solvax holding solenoid hasn't been activated by the control unit. Also, the vacuum switching solenoid is in its de-energized mode, and vacuum is sealed off at the solenoid, preventing the vacuum actuator from receiving vacuum. The engine is now idling at its normal curb setting. Let's assume that the driver has now activated the air conditioning system. When the air conditioning compressor is energized, the control unit receives this input immediately. The control unit sends an electrical signal to the holding solenoid, energizing the solenoid. Now the holding solenoid won't allow the throttle to drop past a predetermined position when the driver removes his foot from the accelerator. Our example is a situation where the air conditioning system is operating, but the system responds in this same manner when the defroster grid or the manifold warm-up device is activated. The reason for this is simply that the control unit circuitry for each of these 3 inputs is identical. The holding solenoid maintains an adjustable throttle position which must be set to provide these idle speeds, which represent an increase of 100 RPM over the normal curb speed settings. Obviously, the RPMs must be above these limits when the air conditioning system is activated for the holding solenoid to maintain these speeds. However, the engine idle speed might be below these limits when the air conditioning system is activated. Also, other loads may cause the idle speeds to drop. For example, an increase in power steering pump pressure could cause the idle speed to drop, even though the holding solenoid has been activated. So, the idle speed must now be raised. The system's vacuum actuator reacts when idle speed drops below these limits. Manual transmissions, 435 RPM plus or minus 10, and automatics, 462 RPM plus or minus 10. When these limits are reached, the speed switch comes into play. The coil signal tells the speed switch that the idle speed has dropped below the lower limit. The speed switch circuit then grounds the vacuum switching solenoid. When grounded, the solenoid allows vacuum to pass to the vacuum actuator. The vacuum actuator now kicks the throttle open further and the idle speed is raised. The control unit allows this kick to last for only 1 second or until an upper RPM limit is exceeded. Upper limits are manual transmissions, 1,175 RPM plus or minus 150, and automatics, 1,000 RPM plus or minus 100. The last engine operating condition to discuss is a cold ambient temperature situation. When the temperature at the ambient temperature switch is below 55 degrees Fahrenheit, the switch grounds the circuit to the vacuum switching solenoid. The solenoid allows vacuum to pass to the vacuum actuator and the kick is activated. The service requirements of the idle speed control system are minimal, but you will need to familiarize yourself with a new idle speed adjustment procedure and the diagnosis steps used to correct a faulty system. These procedures are contained in the AMC and Jeep technical service manuals. The idle speed adjustment is also detailed on the pocket-size reference card that's included in this training kit. The idle speed adjustment procedure is a simple one, but it does differ in some important ways from the procedures you're familiar with. The first step in the new procedure is to connect a tachometer and let the engine idle until it reaches operating temperature. Make sure that the choke and the manifold heater are off before you check the curb speed setting. Disconnect the vacuum hose from the Solvac's vacuum actuator. Also, disconnect the holding solenoid's electrical connector. Observe the idle speed. It should be within the ranges mentioned earlier. If your reading is not within specification, adjust the curb or slow idle adjustment screw to obtain the correct setting. Remember, the slow idle adjustment screw should be adjusted, not the fast idle screw. Next, apply a direct source of vacuum to the vacuum actuator. With the vacuum applied, you can adjust the speed that will be maintained when the vacuum actuator boosts the idle speed. Turn the vacuum actuator adjustment screw on the throttle lever to establish the specified setting. For vehicles equipped with manual transmissions, the correct setting is 900 RPM. Automatics should be set at 800 RPM. When you've completed the vacuum actuator adjustment, remove the direct vacuum source. The next step is to establish the speed at which the vehicle will idle when the electric holding solenoid is energized. Use a jumper wire from the battery to apply 12 volts to the holding solenoid. If the vehicle is equipped with air conditioning, turn it on to properly load the engine. Then open the throttle manually, as shown here, to allow the holding solenoid's throttle positioner to be extended. With the throttle positioner extended, observe the idle speed. It should be within the ranges identified earlier. If not, adjust the holding solenoid adjustment screw to obtain the correct setting. The idle speed adjustment procedure is now complete. You can remove the 12-volt jumper and reconnect the vacuum hose to the vacuum actuator and the electrical connector to the holding solenoid. The 6-cylinder's carburetor has some tamper-resistant features for 1981, features that were added in response to regulations established by the Environmental Protection Agency. A permanently affixed choke linkage housing is installed, and the choke cover is riveted in place to discourage unnecessary choke adjustments. Normally, the choke should not require readjustment from the original factory adjustment. If a major carburetor overhaul is necessary, the technical service manual contains instructions for performing choke adjustments. The idle mixture screws are also sealed to prevent tampering. The idle mixture should not require readjustment under normal circumstances. In the event of a major carburetor overhaul, consult your technical service manual for mixture adjustment procedures. The 6-cylinder engine also features a new EGR valve for 1981. This new design improves EGR calibration precision. As a result, a more effective balance between emission control and performance is established. Some 1981 AMC and Jeep vehicles equipped with the 6-cylinder engine also feature a modified fuel feedback system. The system is still referred to as the Computerized Emission Control, or CEC system. The modifications are a modified air switching solenoid, the addition of a wide-open throttle timer, and a new microprocessor control unit. We won't go into an in-depth discussion of the system's operation in this film. The 1981 AMC Technical Service Manual provides complete operational and service information. However, there is one feature of this new system that warrants some discussion here: the system's self-diagnostic feature, which is also new for 1981. The self-diagnostic feature flashes this light on the instrument panel if certain malfunctions develop in the CEC system. The flashing sequence of this light identifies specific trouble codes. These codes can provide you with specific hints that can cut your diagnosis time down considerably. When the self-diagnostic system detects a fault, the trouble code is flashed 5 times. The system does not have a memory feature. If the vehicle owner informs you that the system flashed a trouble code, you'll need to test drive the vehicle to duplicate the operating conditions present when the owner noticed the code being flashed. The code should be flashed again under these conditions. To provide a routine bulb and system check, the light is illuminated when the ignition switch is turned to the start position. When the engine starts, the light remains on momentarily. The AMC Technical Service Manual contains complete instructions for pinpointing the problem source when any of the trouble codes are displayed. It also provides a detailed explanation of the new CEC system's operation. Be sure to study this section on operation before you try to service this new fuel feedback system. Let's pause at this point and review the 6-cylinder engine's emission control changes. All 81 AMC and Jeep vehicles are equipped with a new idle speed control system. All 6-cylinder vehicles use a tamper-resistant carburetor that discourages unnecessary choke and mixture adjustments. A new EGR valve provides a more effective balance between emission control and engine performance. And finally, a modified fuel feedback system is used on some 6-cylinder vehicles. This system has a self-diagnostic feature that offers a substantial savings in troubleshooting time. The 151 cubic inch 4-cylinder engine, which is used in more AMC and Jeep applications this year, also features some emission control design changes you should be aware of. The 4-cylinder's carburetor also has some tamper-resistant features. Both the 2SE and E2SE carburetors used on the 4-cylinder engine feature choke covers that are riveted in place to discourage unnecessary choke adjustments. The idle mixture adjustment screw is sealed to prevent unnecessary mixture adjustments. A warm-up catalytic converter has been added to Spirit and Concord models equipped with the 4-cylinder engine. This warm-up converter, which is positioned upstream of the 3-way converter, allows the vehicle's various emission control systems to be recalibrated for better fuel economy and performance. All 4-cylinder AMC vehicles are equipped with a new belt-driven air pump. This design, which replaces the pulse air system, also facilitates recalibrations of the vehicle's various systems for better fuel economy and performance. The 304 and 360 V8s used in some Jeep applications also received a couple of the emission control design changes made to the other engines. Both V8s are now equipped with a carburetor that is, to some degree, tamper-resistant. The idle mixture adjustment screws are sealed at the factory. However, the V8 carburetors do not feature a riveted choke cover, as do the carburetors used on the 4- and 6-cylinder engines. The V8 also uses a new EGR valve, which improves EGR calibration precision, resulting in a more effective balance between emission control and performance. And that's it. Major advances in emission control technology and fuel economy are occurring at an ever-increasing rate. It's critical that you're aware of each design change that results from these breakthroughs. Now that you've viewed this film, you should be familiar with the design changes for 1981. The new service procedures associated with these design changes are contained in the AMC and Jeep Technical Service Manuals. Remember to keep the reference card included in this training kit in a handy place. This pocket-sized card offers you a quick reference source for the idle speed adjustment procedure used on vehicles equipped with the idle speed control system.